We're presenting our latest work on robot learning with superlinear scaling. Here's a sneak peek of the results that we obtained, which are in a generalist policy that performs a single task in a variety of objects and scenes. But how did we train these policies? We have two different options. We can collect data in the real world, but this is costly because of expensive hardware, needs large amounts of human demonstrations, and data scales linearly to human hours. On the other hand, we can collect data in simulation. Despite simulation being cheaper to produce and is suited for crowdsourcing, it requires careful design of environments and rewards for training. Instead, we proposed Cacher, a method of crowdsourcing and amortizing human effort for real to sim to real. We leverage the benefits of simulation to avoid the need for expensive hardware. Since the demos are in sim, it's suited for crowdsourcing. We avoid the expensive design by leveraging digital twins of the real-world scenes through cheap scans, and we leverage generalist policies for sublinear scaling of data to the number of human hours. To give an overview, we crowdsource 50 real-world environments. We use the Cacher data collection pipeline to obtain 1,000 successful trajectories per environment, and we distill it into a generalist vision-based policy. In more detail, we start by crowdsourcing a batch of real-world scans where we do autonomous data collection with the generalist policy being trained. The data collected autonomously will then be used to bootstrap RL and simulation on the batch of scans and will obtain a single multitask policy. The resulting policy will work on some environments and fail on others depending by the quality of the initial demonstrations by the generalist policy. Thereafter, for those environments where the policy fails, we query a human demonstrator to provide demos in sim, and we fine-tune a new RL policy on the failed environment. Both of these policies are being used to train the generalist policy, and this process repeats multiple times. Cacher allows us to do zero-shot transfer to novel scenes and objects with high performance and with the number of human demonstrations reducing through training. We are creating this data flywheel where the additional human demonstrations decreases and the performance of the model increases. Training RL policies in simulation leads to robust policies. We show that generalist policies trained with Cacher are robust to scenes, disturbances, distractors, lighting, and multiple objects. Furthermore, we tried Cacher on another task of putting boxes on the cabinet, and we showed that with few shot we obtained similar scaling laws as with other tasks. We also tried it on an articulated environment on the task of opening the cabinet with similar scaling laws. Finally, we propose a novel fine-tuning technique called scan deployment fine-tuning, where we start from a base policy with suboptimal performance in a given task. We use it to collect a set of demonstrations in simulation, and we fine-tune with reinforcement learning. Then we can fine-tune back the base policy and we transfer it to the real world. We obtain significant improvements upon the base policy. We also show that through Cacher, when we improve a policy in simulation, it translates to an improvement in the real-world setting. To finish, we recognize that Cacher is not perfect, and we show some of the failure modes.